Hi, it's Bruce, and welcome once again to my Colorado Rocky Mountain lab. And today we are taking a look at a Rockland Model 5100. Also was made by WaveTech. WaveTech and Rockland, one and the same. More familiar though with the Rockland name assigned to it. So this Rockland 5100 is a 70s version of a direct digital synthesis generator. You'll notice, the barrage of dials we have here. So we have 3 dials for down to the millihertz, 3 dials for hertz, and 3 dials for kilohertz, and 1 dial that allows us to select between 0 and 1. And when you're on 0, there's no multiplication factor. The factor is 1, and you're reading directly what the frequency is, and you put it on 1, you add 1 megahertz to it, and all of the readings after that will appear. It is a working unit. It's a very nice looking unit. The fact that it's working is actually fairly amazing for its age, and for another reason, and I'll show you that here in a moment. Nice wire stand. And as you can see on the bottom here, we've got 4 nice feet and a wire stand. No surprises there. Good looking. And we'll give her a spin around. I've taken the top off, as you can see. In fact, I'll put it out of the way here so it won't fall. And we've got to look at the back. 1 megahertz output, a variable output, a fixed output. A couple of adjusting holes, fan holes, some kind of a port for communications. We'll check into that. And made in USA by Rockland Systems. It's got the serial number and so on. But let's take a look at the inside of this thing. This is the other reason why I was saying it's kind of amazing that the thing is working. Look at the number of chips in this thing. It's amazing. This was an early 7400 TTL series piece of work. This was the stuff I was learning about when I learned digital back in the 70s in college. We have all of the switches up front for the selection of the frequency. We have a row of switches, push-in switches, that are connected to this attenuator board. It gives us our different attenuation values up to, I think it was 40 dB. We can look at that. Basically, all of the digital circuitry for division, I don't know, up to 1,000,000. And a digital to analog converter. Not sure, I believe it's an 11-bit, but I've got to check into that. We have a crystal oscillator, so we have a maintained top frequency that we can divide and get all of our timing accurate. 3, I believe there are 5-volt regulators here at least an amp apiece, so you've got at least 3 amps, maybe more. A big PAM motor to keep everything cool. Good sized transformer to supply all the power, all the filtration you got. This board here is the scanning board, scans all of the switches and then sends all of the switch setting information back to the digital circuitry, which then goes back to this little read-only memory. It's a 512-bit read-only memory that collects the data and then provides it to the circuitry for further processing. So pretty amazing. Nice and clean on the inside. I did have to remove just about all of the socketed. That's another thing. These are socketed. I removed all of the ICs one at a time, cleaned up all of the pins, and then resocketed them. So let's get a look at this thing, huh? While it's working, go ahead and turn around. There's your cooling fan. And we'll put ourselves a lead on. Okay, let's go from $999 to $800. 7, 6, 5, 4, 3, 2, 1. Here would be 99.999, so 100 hertz. Okay, right now I've got it dialed into 678901. Just pick those at random. We've been on long enough now that the unit has warmed up. The crystal oven is pretty much stabilized. There's our waveform. And our frequency counter is reading 678-901-03. But 901. Let's go ahead and dial in a 2. Make it 902. 2,000th of a hertz more. Stabilized waveform. 678-902-01. It takes a special frequency counter to even be able to decipher that. And that Philips is one that will do it. Basically one that utilizes a microprocessor to determine the time difference between the cycles and give you the result instead of just counting the cycles. So again, very attractive unit, very interesting in its concept and design at the time. I totally can imagine this is a project back in the late 70s, early 80s. And the performance is excellent. Let's go ahead and put ourselves at 1,000,000 hertz. That would be like all nines. Okay. We are all nines now. So 999,999.999 hertz. And we need to range up on the scope to even be able to see the waveforms. Here they are. Let's make them just a bit brighter. And we can see on the frequency counter 999,999.97 kilohertz. I wonder if I was to give it some more time, would it? I don't know if it would improve that or not. Probably not. Oh, there we go. 999,999.99. All nines. We are missing one 9 at the end, and we can't read that because there's not enough digits, but it's there. So intriguing, isn't it? Well, it's possible that you might be asking the question, why would I be interested in anything that gives me a frequency down to 1,000th of a hertz and produces it? Well, if you're interested in studying vibration analysis, certain types of equipment would produce vibrations that are very very low. Maybe another thing would be earthquakes. You want to try and analyze the vibration of something that might be sub a hertz anyway. And here's an example of actually being able to measure that. I mean, I've got right now, I'm producing a frequency of 0.145. Why am I doing that? Well, I've got this chemo variable filter set up here, and I have it set up so I have a high pass and a low pass filter in series, and I am passing frequencies that are uh, greater than zero point 0.1 hertz but are less than 0.19 hertz. And the average of that's about 1.45. And what I'm seeing up here is that slowly moving dot on the screen. I am at 0.5 volts per division, so we are going up and down approximately 1.5 volts. So this is 3 volts peak to peak that I am seeing, and I am working at a frequency of about 0.145. So 145, that's what I dialed in. So okay, show me that that means anything to me. Well, let's say we tried to go to a tenth of a hertz more. What would happen? So I'm going to raise it right now, and what we're going to see is that our resonance is going to dampen, and we'll start to flatten out. Right, there we have, we flattened out. Well, that's a tenth high. Let's go back to 0.145 and we should see ourselves come back into resonance. Yeah, we see it starting to swing. There we are. We're back into resonance. Now I'm going to drop myself a tenth of a hertz. So now we're at 0.45 hertz. And once again, we should see ourselves dampen and begin to go flat. And we see it happening. There we go. And if I go back again to 0.145 by adding a tenth, I'm going to see myself come right back into resonance again. So I could band pass 0.145. I've measured it. I've adjusted myself. I know I'm capable of passing it. I'm getting plus or minus 1.5 volts peak, and we're going 3 volts peak to peak. And that's something that I could amplify and study. So, I mean, it's just opens the door. I don't know. Maybe you're studying whales and their vocal habits, or could be sound produced by wind shifts or waves, or sea waves. Something like that. Fascinating that it works, though, huh? This chemo's quite a unit. Frequency to the thousandth of a hertz, up to 2 megahertz. Completely dial selectable in 9 digits. Nice set of attenuators. A adjustable level control, a 1-volt output. We got a rear output. Excellent unit. All right, thanks for watching.